Okay, so let's look at hybridization, the concepts of hybridization and why hybridization is needed. For us to understand why hybridization is needed, we need to look a bit in the brief history of chemistry. So what is hybridization about? Okay, why do we need to even introduce this concept versus the valence bond theory model? Now, the valence bond theory model states that sigma bonds are formed through head-on overlap of orbitals, either s and s orbital, p and p orbitals, or s and p orbitals, while pi bonds are formed through sideways overlap of p orbitals. So for example, this type of bonds between C and H over here, this is a sigma bond, okay? And if there are two bonds, the first bond will be a sigma bond, the second bond will be a pi bond. If there are three bonds, the first bond will be a sigma bond and the two other bonds will be pi bonds. Now let's look at how the sigma bond is being formed. Okay, so I'm going to let you watch a very quick video. So these are head-on overlaps of sigma S and P orbitals. Okay, S and S, P and S and P. Let me show you again. Head-on overlap of S and S, S and P and P orbitals to form the sigma bond. Now, what is the problem with this model? Consider a methane molecule. There are 4 single bonds, which means there will be 4 sigma bonds. And sigma bonds are formed from head-on overlap of, based on valence bond theory model, they are formed from head-on overlap of s orbitals or p orbitals which have unpaired electrons. Once again, take a look at this. They are formed from head-on overlap of s and s orbitals, s and p orbitals, and p orbitals. And each of them must have 1 lone electron. So in order for carbon to form 4 single bonds, it must mean that carbon must have 4 unpaired electrons. But if you look at the carbon in the ground state, the electronic configuration is 1s2, 2s2, 2p2. There are only 2 unpaired electrons, which means that carbon by right should only be able to form 2 sigma bonds. So how do we overcome this problem? We just need to excite one of the electrons from the 2s orbital into the 2p orbital. We call this the excited carbon. You will now realize that there will be 4 unpaired electrons, allowing you to form 4 sigma bonds. Okay, now what is the problem with that? The electrons are in the s and p orbitals, and p orbitals are 90 degrees away from each other, which means that the bond angle you will expect will also be 90 degrees. But we know that CH4 methane molecule is 109.5 degrees. So this is why we introduce something called hybridization. Okay, hybridization means a hybrid model which combines the s and p orbitals to form new hybrid orbitals. So for example, okay, you have your excited carbon. If you combine your s and p orbitals, okay, you combine one of the s and 3 of the p. If you combine them together, okay, it will be called sp3. Okay, we combine them together. It's called sp3 because we use 1 s and 3 p orbitals. We combine them together because we use 4 orbitals. We will end up with 4 new hybrid orbitals, which are called the sp3 hybrid orbitals. And now, because these 4 orbitals are all equivalent, they can be put together with the 109.5 degrees bond angle. Okay, so another way of representation, if you combine the s and the p orbitals, these are the energy profile diagram. By right, s and p have different energy levels, but after the hybridization, they will be combined to form one common sp3 hybrid energy level, which are 4 equivalent hybrid orbitals. Okay, so now once you have your 4 hybrid orbitals over here, the one that I'm circling here, okay, once you have your 4 hybrid orbitals with 109.5 degrees, this is where your hydrogen comes in to do your head-on overlap to form your CH4 molecule. Okay, and this is how, example, ethane molecule looks like. So each carbon here is sp3 hybridized, and the hybrid orbitals are used to do the head-on overlap to form the sigma bonds. Let me show you a quick video. Okay, so this is the s and the p orbitals. If you promote one of the s to the p, okay, I'll show you again. You promote one of the s to the p orbitals. Now you have 4 equivalent hybrid orbitals. Now, in terms of the orbitals, how do they look like? So over here, at first, you have an s, the yellow one, and you have 3 p orbitals. After the hybridization, they will be combined to form new hybrid orbitals, which are in green now. So these are 4 equivalent hybrid orbitals, which can be used to form your head-on overlap. Okay, so this will be 109.5 degrees. And once you form your 4 equivalent hybrid orbitals, this is where your hydrogen comes in to do your head-on overlap to form your methane molecule. So each of these represents the sigma bond formed. So this is how sp3 hybrid orbitals are formed. The sp3, the 3 means that you use 3 p orbitals and 1 s orbital to combine to form the new equivalent hybrid orbitals. Now, this 1 minute of chemistry. See you the next time.